Finally. Honestly, that coupled oscillators experiment always just fries my brain,
Tell me about it.
especially when you're trying to calculate the damping factor on that old equipment.
You spend half the time just calibrating the instruments, but the T is here, so things are looking up. I noticed the students today, they were really struggling with the idea of energy transfer between the pendulums.
Definitely. And, while we were discussing resonance in the lab, a thought struck me. We treat these forces damping, driving forces on these little springs and pendulums, but what if we just scale it all up?
You mean to a planetary scale?
Yeah, exactly. It's essentially the same physics, isn't it?
You're thinking about tides.
Exactly. Tides. I've noticed, even with our BSc students, their approach to tides is so casual. They think it's just fluid dynamics. The moon pulls the water, high tide, low tide, end of story.
The geography textbook version.
Right. But as physicists, we know how incomplete that picture is.
Incomplete is an understatement.
Yeah.
It's misleading. From a physics perspective, tides are basically these silent killers of orbital energy. It's not just about fluids. It's a severe case of rigid body dynamics.
It's gravity, viscoelasticity, conservation laws all working against each other.
Exactly.
And it's all about energy dissipation, whether we're talking about the Earth-Moon system or Jupiter's moon Io, which has basically become the solar system's biggest heat engine. The mechanics are the same. So since we seem to have a long tea break today, let's do this. Let's do a deep dive into tidal forces. Not the watered-down version, but the real, rigorous orbital mechanics version for our students.
I'm in. Let's really unpack the vector math behind it, because students always get confused about why the bulge even forms if gravity acts on the center of mass. They think the moon is just lifting the water.
Good point. Okay, so let's start from first principles. Newton's law of gravitation. Your basic F equals gmm over r squared. Now, in orbital mechanics, we usually treat bodies as point masses to make our lives easier. You take the distance from the center of mass and you solve. But for tidal forces, that approximation it fails.
It completely breaks down. The point mass approximation is only valid as long as the distance, r, is much, much larger than the size of the body itself, r.
But when you're talking about the Earth and the Moon, the Earth's radius is significant compared to the distance. You have to consider the gradient.
That's the key word.
Right. Let's visualize this for anyone listening. Imagine you're at the center of the Earth. The moon is attracting you with a specific force. Now imagine you're on the Earth's surface, at the closest point to the moon, the sublunar point. The distance there is smaller. It's r minus the Earth's radius, so obviously the gravitational pull is stronger.
And of course, the point on the opposite side, the anti-lunar point, is further away, r plus r, so the force there is weaker. The tidal force is essentially the difference in these forces relative to the center of the Earth. It's a differential.
And if we actually do the math, if the gravitational force depends on 1 over r squared, and we take its first derivative with respect to distance to find that gradient, the tidal force should be proportional to 1 over r cubed.
Spot on. The Sander texts highlight this. The tidal potential, psi, drops off as the inverse cube of distance. And the implication of that is huge.
It means it's extremely sensitive to distance.
Extremely. If you double the distance, the force of gravity drops to 1/4, but the tidal force drops to 1/8.
Which is why the sun, despite being so much more massive, has less of a tidal effect on us than the moon does. Its mass is huge, but it's so far away that the 1 over r cubed factor just kills its effect.
Precisely. The sun's tide-raising power is only about 45% of the moon's. Now, what's the physical effect of this gradient?
It's a stretching force.
Stretching. The Earth stops being a perfect sphere and becomes, well, an ellipsoid. It's pulled along the line connecting the Earth and the moon, and that's what we call the tidal bulge.
Okay, and this is where students always ask that question. Sir, I get the bulge on the side facing the moon because the pull is stronger, but why is there a bulge on the opposite side?
Ah, the classic confusion. There are a couple of ways to think about it. You could use a centrifugal force frame, but that can get messy. The better way is to think in terms of pure differential forces.
Right.
The center of the Earth is accelerating towards the moon, but the water on the far side is being accelerated less than the center is.
So the center of the Earth basically pulls away from the water on the far side, leaving it behind.
Exactly. So relative to the center, that water effectively bulges outwards. You get two bulges, a dipole effect.
Okay.
Now here's the twist. If the Earth were ideal, a perfect fluid, zero viscosity, zero friction, this bulge would always point directly at the moon. It would be perfectly aligned with the line of centers. An instantaneous response.
But the Earth isn't ideal. We're talking about real-world physics here. The Earth is messy. It has oceans, continents, and a solid mantle that isn't perfectly elastic.
Which means it has what we call viscosity, or internal friction.
And this friction introduces a time lag.
A time lag. This concept is absolutely crucial. See, the Earth is spinning really fast, one rotation on its axis every 24 hours, but the Moon is orbiting slowly, about one lap every 27 days. So obviously the spin is much faster than the orbit.
So the situation is the Earth's material, the rock and the water, forms this tidal bulge, but the Earth's fast rotation tries to drag that material ahead of the Moon.
Exactly. The friction between the ocean floor and the water and the internal friction in the mantle, it drags the bulge forward. So you can imagine the bulge is physically dragged ahead of the Moon by some small angle.
And that misalignment, that's what changes the entire game. Because now you have a geometry problem. The Moon's gravity isn't pulling on the effective mass in a straight center-to-center line anymore.
No, the Moon tries to pull that misaligned bulge back.
Yeah.
And from a vector calculus perspective, whenever your force vector and your position vector are not parallel,
You generate a torque.
you get a torque. And since the bulge is leading, the Moon pulls it back, which acts against the Earth's rotation. It acts like a cosmic brake.
Tidal braking. So Earth's spin angular momentum is decreasing. Basically because of friction, our days are getting longer.
Yep, the Earth is slowing down. Current astronomical data shows the length of the day is increasing by about 1.7 to 2.3 milliseconds per century.
2 milliseconds per century sounds like nothing. A student might think, who cares? But on a geological timescale, that's huge. I was reading the source notes on tidal rhythmites, these ancient sedimentary rocks that preserve tidal layers.
Ah, yes, the Mansfield sediments.
Correct. They show that 620 million years ago, at the end of the Precambrian, a day on Earth was only about 21.9 hours long.
Absolutely. And if you go back even further to when the Earth first formed 4.5 billion years ago, models suggest the day might have been just 6 or 8 hours long. The Earth was spinning wildly fast.
And it's been slowing down ever since because of this tidal friction. Okay, but fundamental law of physics, conservation of angular momentum. If the Earth's spin momentum is decreasing, where is that momentum going? It can't just vanish from the system.
Great point. Nature has to balance the books. If the Earth is losing it, the Moon must be gaining it. It's being transferred into the Moon's orbital angular momentum.
So to increase its orbital angular momentum, the Moon has to move into a higher orbit.
It has to spiral outwards.
The recession of the Moon?
Yes. The retroreflectors left by the Apollo missions, basically high-tech mirrors, we can bounce lasers off them and measure the round-trip time with incredible precision. Lunar laser ranging.
And the data confirms it.
It confirms the Moon is moving away from us at roughly 3.8 centimeters per year.
3.8 centimeters. That's about the speed your fingernails grow. It's so strange to think about, but our own Moon is literally being pushed away by our tides.
Slowly but surely. But here's a trap students often fall into in exams. Angular momentum of the system is conserved, but what about the total mechanical energy?
It can't be conserved. Not if we're using the word friction. Friction means dissipation. It's a non-conservative force.
Correct. The total energy is decreasing. Mechanical energy is being converted into heat. Calculations show that roughly 3.7 terawatts of power are continuously dissipated in the Earth-Moon system.
3.7 terawatts is massive. That's comparable to the total power consumption of all human civilization. Where is all that heat going? Are the oceans boiling?
Fortunately not boiling, but they are warming slightly. And surprisingly, very little of the dissipation happens in the solid crust. Most of it happens in shallow seas, from the turbulence and friction between the ocean bottom and the water.
So places like the Bering Sea, the Patagonian Shelf?
Those are the hot spots. They're essentially the brake pads for the Earth.
Wow. The brake pads of the Earth. That's a great analogy. So the Earth's rotational kinetic energy is being converted into turbulence in the Bering Sea. Okay, so that's the Earth-Moon system. Things are relatively gentle. Let's take the physics to the extreme. Let's talk about Jupiter and Io.
Io. The pizza moon. My favorite celestial object for thermodynamics problems.
Io is just bizarre. Students expect it to be like our moon, a cold, dead, cratered world. But when Voyager first saw it, it looked, well, like a moldy pizza, yellow, red, black. And it's constantly erupting with volcanoes.
It's the most volcanically active body in the entire solar system, and the question is, why? Physics says small bodies should cool down faster. Io is about the size of our moon. It should have gone cold billions of years ago. The heat from the sun is negligible out there, so what's the heat source?
It has to be tidal forces again.
Yeah.
But the mechanism is a bit different from Earth, right? Here, the tides are causing braking. On Io, they're causing heating. And that's where resonance comes in.
Yes. It's called the Laplace resonance. Io isn't alone. Behind it is Europa, and behind Europa is Ganymede. And their orbital periods are in this perfect integer ratio 1 to 2 to 4.
So for every one orbit Ganymede makes, Europa makes exactly 2, and Io makes exactly 4.
Exactly.
And what's the physical implication of that? It can't just be a numbers game.
No, it's a periodic gravitational kick, like pumping a swing at just the right moment. Every orbit, at a specific point, Europa and Ganymede give Io a little tug. Now, tidal dissipation would normally want to make an orbit perfectly circular.
Right, eccentricity goes to 0.
And in a circular orbit, tidal heating is 0 because the distance is constant. But this resonance prevents Io's orbit from circularizing. It forces it to maintain a slight eccentricity of about 0.00041.
And eccentricity means the orbit is slightly elliptical, so Io's distance from Jupiter keeps changing.
Precisely. When Io is closest to Jupiter, at periapsis, the tidal force is massive, that 1/r³ effect, and the tidal bulge gets huge. When it moves further away to apoapsis, the force weakens and the bulge shrinks.
So Io is physically changing its shape continuously. It's being squeezed and stretched on every single orbit, which is only 42 hours long.
Like rhythmically crushing a rubber ball.
If you do that fast enough, it'll get hot.
Exactly. That's internal friction in the rock. That's what's happening to Io. The process is called tidal dissipation. And the math behind the heating rate is fascinating. Do you remember the formula?
The heating rate is proportional to eccentricity squared over the semi-major axis to the 6th power. And it has that term I always found poetic, the love number, specifically the imaginary part I'm of K2.
Named after Augustus Love, yes. The love number K2 is this dimensionless value that tells you how deformable a body is. If K2 is 0, it's a perfectly rigid solid. If it's 1.5, it's a perfect fluid.
And Io's observed K2 is something like 1.29.
Which is incredibly high. It implies it's incredibly soft inside, almost behaving like a fluid sphere.
But the aha moment for a physics student should be why we're discussing the imaginary part of the number.
Right. In complex numbers, the real part is the elastic response energy storage. The imaginary part is the viscous response energy loss. It's just like in AC circuits. The imaginary part here represents the phase lag.
So the bigger the imaginary part, the bigger the phase lag, and the more heat gets generated.
Correct. The high value suggests Io's interior is partially molten. There's a debate in the sources about whether it's a full-on magma ocean or just a highly melted asthenosphere. But the conclusion is Io isn't behaving like solid rock. It's behaving like a viscous fluid because of all this heating.
And the heating rate is enormous.
It's around 10 to the 14th watts globally. The heat flow from the surface is about 2.5 watts per square meter. For context, Earth's internal heat flow is measured in milliwatts. Io is literally cooking itself from the inside out, powered by orbital mechanics.
And all that energy, ultimately, where is it coming from? Conservation laws still have to apply.
Good question. It's ultimately being extracted from Jupiter's rotational energy. The resonance maintains the eccentricity, and the eccentricity drives the heating. Jupiter's spin is melting its own moon.
That's amazing. Gravity isn't just a passive force holding things together, it's an active engine. So if we fast forward this whole process, Earth, Moon, Jupiter, Io, what's the end game? What's the equilibrium state?
The ultimate fate is tidal locking or synchronous rotation. That's the minimum energy state.
You mean when the rotation period and the orbital period become exactly the same?
Like our moon.
It always shows us the same face.
Exactly, because billions of years ago, Earth's gravity put the tidal brakes on the moon until its spin slowed down to match its orbital period. Once spin equals orbit, the tidal bulge becomes stationary on the body's surface. There's no more internal motion, no more friction, no more torque. Evolution stops.
So the moon is locked to the Earth. Why isn't the Earth locked to the moon yet?
Inertia. The Earth is massive. Its moment of inertia is huge. It takes a very, very long time to slow it down. The moon was small, so it locked relatively quickly.
But the process is still ongoing for us.
It is. The Earth is slowly trying to lock to the moon. Estimates say that billions of years from now, the Earth's day and month will be the same length, about 47 of our current days.
So technically, a time will come when one side of the Earth will always face the moon, and the other side will never see it.
Just like Pluto and Charon, they're the best example of a tidal endgame. They are mutually locked. They just stare at each other as they dance. Earth and moon are headed that way.
But there's a practical problem.
There is. Stellar evolution gets in the way.
Let me guess. The sun.
The sun. This tidal process for the Earth-Moon system is so slow that before it completes, the sun will enter its red giant phase. In about 4.5 billion years before the Earth can fully lock, the sun will expand, vaporize the oceans, so no more friction, and probably destroy the whole system anyway.
So nature won't let us reach that perfect, boring equilibrium. Talk about a tragic ending.
Well, in physics, equilibrium is often the boring state. The dynamics are where the fun is. Look at Saturn's moon Enceladus, same mechanism. A resonance with Dione maintains a subsurface ocean. The heating is less intense than Io, but it's enough to power those ice geysers.
Same physics, different outcome based on the parameters.
It's like,
Okay, my tea is almost gone, and I think the next lab section is waiting. Let's wrap this up. If we had to summarize this whole discussion, a key takeaway for the students, what would it be?
I think there are three main points. 1, don't think of gravity as a static force. On finite bodies, the gradient matters. It creates a bulge that depends on 1 over r cubed.
Okay.
2, real bodies aren't perfect. Viscosity creates a time lag, a phase shift, and that misalignment creates the torque that drives all this evolution.
Right.
And 3, nature balances the books through dissipation. Angular momentum is conserved by transferring from spin to orbit, but mechanical energy is lost as heat. And that heat can power geology, like on Io.
And the biggest realization for me today is that time itself, the length of a day, isn't a true constant. It's a variable that depends on friction in the Bering Sea.
It absolutely is. And here's a final thought for anyone listening. We said energy is dissipated on Io, but think about Earth. Every time you see the tides come in, every wave that crashes on the shore, where does that energy come from?
It's not free energy.
It's not. It is ultimately the Earth's rotational kinetic energy being drained away to make that splash.
So our planet is losing its spin, in a way, just to push the moon away.
Yes. So next time you check your watch and feel like time is running out, just remember, the moon is literally stealing milliseconds from you every single day. It is physically stretching your seconds.
Chuckles. I'm going to use that excuse the next time I'm late for the department meeting. Sorry, tidal drag was exceptionally high today.
Good luck with that. The department head is also a physicist. He'll just calculate your angular momentum and give you an even harder time.
All right, let's head back to the lab. I think it's time to check the love number on those coupled oscillators.
Let's go calibrate reality.
Thanks for listening to this deep dive. Keep calculating and keep thinking.